This third video is to relate Kepler's third law of planetary motion to how it manifests in STK. Kepler's third law of planetary motion got a lot more complex, actually, and was one of the most mathematical in its applications. Other videos on this might actually be useful to look into to get more information on it, because there are some really cool mathematical relationships. Kepler showed mathematically that the period squared over the semi-major axis cubed of a planet was equal to the same number for every single planet. Now, I want to talk for just a moment to kind of really get that across. It was almost as though there was one magical number that appeared to be built into the night sky. All the planets, when you analyze them, would give you back this same number, which at the time was very, very confusing. Or at least something worth a lot of additional study. It would take a lot longer until a person named Isaac Newton would come in and explain why that mathematical relationship existed. Now, we're not going to go through all the math on it, but we are going to show you how it manifests here in STK and ways that Kepler's third law could be useful in some of the stuff that you're working on. In short, you would say something along the lines of the semi-major axis and period of an orbit are related mathematically. Might be a simpler way of doing it. A takeaway on this is a higher orbit, in other words, a bigger orbit, will take longer to complete one full orbit. That's what a period is. Period is the time for one complete rotation. And semi-major axis, as we looked at in some of our previous videos, kind of deals with the size of your orbit, how big it is, how far out it is. All right, let's switch over to STK. So, one of the main ways that I want to show Kepler's second law of planetary motion manifesting is basically taking a look at adjusting the semi-major axis and checking the period. But that's one of the things where, okay, how do you check the period? Well, in your orbital parameters, you can go over to the semi-major axis and drop it down. We talked about things like apogee radius and apogee altitude, but look at the next one down, period. 6,750, roughly, seconds for this period. In fact, this is how we can tell how long it will take. Well, 6,700 seconds, well, there's 60 seconds in a minute, so if I divide this by 60, I would end up with minutes. Well, that would be 6,700 divided by, in fact, let's just change this. Let's make it 6,000 seconds. Ooh, we're in pretty close. Now that means that it will take us 1,000. Am I doing that right? 1,000? Nope, 100 minutes to orbit. Because 6,000 divided by 60 would leave me with 100. So that would leave me 100 minutes. This has an orbital period of 100 minutes. So if I watch, it starts at 1,700 hours. If I watch for the time it takes to do one complete orbit, it should come back 100 minutes later, which is an hour and 40 minutes, which is about what we saw there. Great. So this is what we can actually do. Our period, let's go to a higher period. Let's say something that's 10 times as long. It takes 1,000 minutes to orbit. Well, I don't see the orbit anymore. Well, that's because it's much farther out. When you go farther out, it will take longer to complete one orbit. Which honestly makes a lot of sense if you think back to Kepler's second law. We know that the farther out the satellite is, it takes longer or it moves slower. So not only is the satellite moving slower out here, but on top of that, it's going around a bigger orbit. So if it's moving slower the entire time, and it's in a bigger orbit, of course it's going to take a lot longer to complete one complete orbit. What makes Kepler's third law so important compared to the second law, even though they seem to draw the same conclusions, if your satellite's out farther, it moves slower or takes longer to complete an orbit, Kepler's third law brings in an actual very rigorous mathematical approach, something that was a mystery for some time, like I said, until Isaac Newton came in and explained with his presentation of the ideas of gravity and its mathematical modeling, why this actually takes place. Now, ways that this could be very useful. Well, there is a type of orbit that's actually really useful and used quite a bit. Let's see, we want a period of 24 hours. Let's get something that has a period of 24 hours. Now, what I need is that in seconds, or I can do this drop down here and I can switch it over to hours. This has an orbital period of 16 2/3 hours. Let's bump this up to 24 hours. I'm going to click apply. And now I've got this, but here's the interesting thing. So we've got our orbit right here. Our satellite is right above, say, the South Pacific. Well, not quite south because it's equatorial. But I'm going to press play. And as I watch it, every time it passes me, it's above the same spot on Earth. In fact, let's take a look at our 2D graphic and see what our satellite looks like. We don't have a ground track anymore because the satellite appears to be completely stationary. Well, why would that be useful? Well, if I wanted it to talk to, I don't know, the United States, well, this is probably not a great spot for it because it's way off over the Pacific Ocean. But I could go in and I could adjust some of the orbital parameters, and here's where some of the orbital parameters would come in handy. Let's go with, I don't know, a true anomaly of 40 degrees. Let's see. Did I get that right? Ooh, not quite. Let's go with 180 degrees. Maybe I should have come more prepared. Here's what I'm going to do. Tile vertically so I can see this a little bit better. Oh, I went a little too far. Now I just went past South America. Okay, let's go with, I don't know, 110 degrees. There we go. Now, one thing that you'll notice is right now it's above the equator and it can stay in that spot. This is a very special orbit called a geostationary orbit. It's an orbit that has an orbital period of 24 hours and is directly above the equator. So, for the most part, the satellite appears to stay in one point of the sky. Now, I will talk about this a little bit because we use these orbits a lot. In fact, if you have satellite television, things like DirecTV or Dish Network, you're probably getting your television right now off of one of these satellites. Interesting to note, if you ever take a look around, or if you have one of those satellites, look which way it's pointed off of your house. It's always pointed to the south. Now, it may not be due south. It depends on where above the equator the satellite is. In this case, depending on what part of the United States you're in, if you're in the central area, then this satellite, you'd probably point it due south. But if you're in New York, you might point it to the southwest, and if you're in Oregon, you might point it to the southeast. But all of the satellite dishes will actually point southward. Now, this is a geostationary orbit where the satellite appears to stay in one spot the entire time. Let's change our orbital inclination, and we can get what's called a geosynchronous satellite. Now it makes a figure 8 on here, and that's because sometimes it's above the equator and sometimes it's below. We can't get something where it stays just right above, say, New York City, because the center of the orbit must always be at the center of the Earth, which means if you've got it tilted up to the north, it has to at some point go back south. So these geostationary satellites, the geostationary are specifically above the equator in an equatorial orbit, but these geosynchronous are still going to stay in the rough area of the sky, so you would be able to see them up in the sky at any point for the most part, but depending on their orbital inclination, you might have to kind of crane your neck a little bit. They'll move in a small figure 8 is how it projects its course onto the ground track. So, these are important things to take a look at. That's also why instead of going with your semi-major axis, how far out you are, you could instead actually just put it straight in the period. Now, why could this be useful? Well, maybe you've got a target that you know you have to see every single day. Well, if you could set it up to try and get your period to be in even increments so that it'll catch it the next day it goes by. Those are some things that you could use with the period. But this is a little bit of Kepler's third law of planetary motion. There's a lot more math that we're not even remotely touching, but the important takeaway is as you get farther out, it will take longer for one complete orbit, one period. Hopefully that's useful.